Hello, welcome. I'm Jim. I'm a recently retired Intel engineer from the Xeon design team. And before that, and for those that remember 90s tech, the Alpha microprocessor design team at Digital Equipment Corporation. Now, I retired about 6 months ago. And as anyone would tell you, a common problem of retirement is what to do with your time. Now, most people like to think when you spend retirement, hey, I don't have to do anything anymore. I could just lie around. But you do have to find something to keep your mind occupied, or you may go insane. And besides, I found just following around and hovering the wife just leads to her being annoyed with me and that. So we're going to today start a new hobby, and that's creating my own server home lab. Now I'm going to do typical things with this home lab, as most people do, and many YouTubers have shown, which is Proxmox and NAS and other things. But I also like to explore AI and machine learning software and that, maybe play around with some of my own models, as well as the freely available silicon design software and that, which kind of harks back to what my job used to be. And besides, after spending 20 plus years working on Linux and being occasionally thrown that bone of a sudo priv or two, I'll finally be able to be king of my own environment, and that's kind of cool because I'll have root privs. So I have in front of me the various parts of the first server I'm going to build for this home lab. And this isn't a sponsored build. I went out and actually bought these parts and paid for them myself. One of them I'll talk about before long, actually a while ago. And during the course of the build and the video, I'll talk about why I chose what I did. So with that, come along, my friends, and let's get started on this build. Let's start the build by addressing the elephant in the room first, which is this big black box and that. This is the chassis we're going to do the build in. It is a server rack chassis. It's Silverstone RM52 in particular, and you can check out a separate unboxing video if you want to see all the details in that. But in a nutshell, this is a 5-unit tall server rack chassis that also could be assembled vertically instead of horizontally if you want it more like a workstation. You can see it can accommodate two 360 radiators for cooling and a variety of other options on that. It can support the largest of the ATX power supplies, as you can imagine, but it also has support for a secondary SFX power supply if you want redundant or 2 power supply units, and it even has support for a standard server 2U redundant power supply. The motherboard has a whole variety of holes for different standout positions and that, so it can support a whole, basically just about any kind of motherboard out there, from regular ATX different sizes to server ones. And as you can see, it supports up to 8 PCIe slots and that, so the full accommodation in terms of multiple GPUs, and it even has a unique bracket for holding down those expansion cards in that. And then finally, while this isn't a NAS case, so it doesn't have a bunch of drive slots, it can accommodate a variety of different hard drives and SSDs in different positions within the case. Now, today I don't have my server rack, so my plan is to build it at first more as a workstation, so it's vertical. We can do a later video on the creation of the rack itself and that. So let's go ahead and start the build by setting this up for more vertical mount by first attaching the feet. But first thing I'm going to do is take off the lid up here on the top. So the lid is held together by a bunch of different screws. It slides back a little to rest, and then we pull it straight up from there. Okay, with the lid off, let's now attach the feet so I can put this in a vertical position and that. So the feet, it comes with 4 of these feet. These attach to the bottom here and that using hardware. We have like a rubber grommet on a screw that we can put on the bottom of the foot and then attach it to the case. It just screws right in. And the nice thing about these feet is they haven't, you can see over here, they have these indents on it. And that way we can have our foot either in the out position like that, or we can actually move it this way to hold it down. So these two indents hold its position. So you can choose to go either way. Now let me go ahead and install the other four. Or it should say the other three. Alright, with the feet all installed, next we can install the handles that go on the top. That makes carrying the workstation a little easier. So the first step is to actually screw the handles onto the support brackets. The screw is nice and recessed, so it's not protruding at all. So now we can go ahead and attach it to the case itself. With both handles installed, let me put the front cover back on. And now we can easily see, or we can take the case and lift it and put it right here on the table. The next step I want to do is actually remove the motherboard tray. It makes it convenient. Inside here there is the motherboard tray on the bottom that can be removed, so we can assemble the motherboard outside the case so I don't have to fight all these kind of walls and that. So in order to get the motherboard tray out, I'm going to have to first remove this GPU or PCIe expansion card bracket or support bracket and that. So let's put this back down on the table. Now the ingenious thing about these feet, as you can see, is we can fold them in, and then that makes it easy to lay the case back down on its side. This support bracket it's held together by 4 screws, 2 on each side on it. And the nice thing about the way they've done this is one could actually move this bracket to a variety of different positions. But now we have access to the motherboard tray. We can get that out. Now the motherboard tray is held down by a few screws from the back side. 5 screws removed on the back, we can now remove the motherboard tray from the case, and we can move on to the next part of our build. The motherboard we'll be using in this build is the Asus ProArt Z890 Creator Wi-Fi board. This is a full-featured board that's really sort of targeting to the video editor or workstation type environment. In particular, it has 2 PCIe 5 slots that has bifurcation, which means we can install 2 different GPUs here and have ×8 lanes going to each GPU in that. And for video editors, or for someone like me who might do machine learning, we can really take advantage of the multiple GPUs in that for the processing power. And it also, you note there's a third PCIe slot down here. This is a PCIe 4 slot that has 4 lanes, although it's a physical 16 slot. And in particular, the distance between here and this slot can accommodate a double graphics card, a double slot graphics card, as well as a network card together. And I found that's a little unusual for motherboards, to find something that actually had that spacing in here as well as the bifurcation, the ×8. In terms of the other specs, has 5 M.2 drives. We have one up here that is PCIe 5, and we have 4 more PCIe 4 slots down here. One of them shares its lanes with the SATA drives. The DRAM is DDR5, and they can support up to 256 gigabytes using some new Kingston 64 gigabyte modules. It has numerous high-speed USB, Thunderport, and 10 gigabit on the side, again targeting the creator of the video editor type audience. And you can sort of tell that on this motherboard that the money is really more spent for features and quality than for bling. There's no RGB on this and that, so Asus was really sort of keeping it on note in terms of a workstation build and less of something more of a showcase. Now, at first glance, I was thinking about attaching this to the motherboard tray before I went on to the next steps of the build. But then I remembered I have to put a cooler on it, and the cooler we have to attach from the back. So let's go ahead and do that first. The CPU we'll be using in this build is the Intel 285K. Now, I'm sure this is where I might lose the AMD fans out there from this video and that. But keep in mind, the target of this build is for a Linux headless server, not really a gaming machine. So frames per second isn't really a chief consideration for my build. Instead, what is a consideration for me is the number of cores and the performance. Now, one might say the Xeon or the Threadripper CPU might be more conducive for that kind of build environment. And I would agree with them that it does give a better position. However, going to that level takes us to the next level of the price point in terms of not only CPU, but the rest of the components around it. And besides, I have some personal friends that helped work on these different CPUs while I was at Intel and that, and I feel it's important to support your friends in the work that they do. Now, why the 285K, which has 24 threads instead of the 265K, which is half the money, and only 4 less threads, 20 threads? Well, I felt basically the 4 extra cores or threads might actually make a difference in the parallel processing that I'm doing with the virtual machines and or perhaps the machine learning experiments in that. Time will tell whether I pat myself on the back for spending that extra money or lamenting that decision. Let's first get the CPU into the socket. So to do that with this LGA 1851 socket, what we need to first do is move this lever out so we can open up the socket itself. We can then take our CPU out of its packaging and carefully place it into the socket. Now, one thing you want to note on the CPU itself, if I can get it in front of the camera, is a little notch right here on each side. You want to note where the notches are inside the socket here and line them up, and just carefully and gently just place it right on top as such. And then we can close the case right here, and this pops right off the top, and lock it down. Now, one thing I want to note here is that I decided to forego a contact frame, which is kind of popular out there. At least it was very popular in the previous generation. So a contact frame would be something that you would use to hold down the CPU instead of the standard ILM connection right here and that. Now the pressure points, the reason why the contact frames can be useful in helping to reduce the temperature of the CPU is because this particular ILM, when you lock it down, the pressure points are on the side, and the pressure points can push down hard on it such that it puts a slight bend, a very slight bend on it, and that affects how flat the connection is to the heatsink. But in this particular generation, this is what they call the RL ILM, or reduced load. And essentially what Intel has done is they put shims underneath each side of these the ILM to help reduce the pressure that gets applied here, which means the bending is not as severe as before. So I decided to just go with the standard things in here, and time will tell when we do heat tests and that whether we need to change it out. The particular case that I have and the cooler that I have wouldn't make it very difficult to change your mind down the road. Now the memory you're going to use in this particular build is the G.Skill DDR5 2x48 gigabytes, or basically 2 modules that give us a total of 96 gigabytes of memory. The speed of it is 6,400 megatransfers per second, and the CAS latency, or the CL number, is 32. Now my goal here was to maximize the capacity while still being in 2 slots, and today, as I was doing this build, the highest I can get is 48 gigabytes in a single module or a single slot. Also, 2 slots are a little easier to get up and working and stable of a build, but I might revisit that later as more memories become available and they become cheaper than that. So let's look at why I chose these particular RAM sticks in terms of all the different 96 gigabytes choices that are out there. If we start with the module that I picked, which is DDR5 6400CL32, my goal here is to reduce the latency it takes to read, or how long it takes for the CPU chip to pull a piece of data off the RAM. And obviously the lower the number, the lower the latency, the better it is, the faster we can get at that data. So in order to calculate the latency based on the spec numbers that we're seeing here, we first take that megatransfers per second and we convert it to gigatransfers per second. So that's just simply divided by 1,000 or moving the decimal place over. That way we get a convenient nanoseconds result at the end. Next, we're going to take the 6.4 and divide it by 2. The reason why we do that is because one of the D's of DDR stands for double, or double read rates. And that, so we only are interested in one read or one transfer, so we're going to divide that number by 2. And then next we turn that into a clock cycle time on that. So that's just simply inverting the number, or dividing 1 by the 3.2 number, or a single transfer time. And that gives us the 0.3125. And then finally, to get the latency, we multiply it by the CL number, or the CAS latency number, which tells us the number of clock cycles it takes for the RAM to respond to a read. So in this case, we multiplying that gives us a 10 nanoseconds. Now, if you want to reduce the steps here involved, you can take this more simply as a single equation, which is just 2,000 times the CL number divided by the speed. And if we plug in our 32 and 6400, we get the same answer as 10 nanoseconds. Compare that to some of the other modules that might be out there, because sometimes there's a confusion in terms of picking. Like, one might naturally think a RAM with a 6800 speed is going to be better than a 6400. But it really comes down to this sort of equation, which has to take into account both these numbers in that. So if we start with 6800 with the CL40, which is actually pretty slow, we plug in our numbers, we can see, in fact, the latency it takes to do a read is slower, somewhere between maybe 10 to 20% slower than the RAM before it, despite the speed of the RAM being higher at 6800 than the 6400. In order to get to the same rating, the same 10 nanoseconds with a 6800 RAM, we would have to have a CL34. And if you want to go even faster than our 10 nanoseconds, then another RAM option out there is one at 7,000 with the CL34, and you can see that is now slightly faster than the 10 nanoseconds. Now we're at 9.714. And at the time I made this video, looking at PC Part Picker, I noticed there was one additional one, which is 6600 at CL32, which is in fact the fastest one out there. So, just going by the speed alone, one might not think that the 6600 is in fact the fastest RAM. Now, of course, with all these different options, the next thing you're going to want to do is overlay the price. So if I put the price on it, as of the time that I made this video on that, you can see that many of the different slower equivalent options are in fact more expensive than the one that I chose up at the top, which is at $290. And of course, another ones are out of stock. So often you have to sort of take this all into account to pick the right one. Now, as I said, with price being attractive on the first one, with the latency being reasonable, and then finally with the Intel's own specs on the CPU saying memory speed is supported up to 6400, it made for an easy choice on the top. Okay, let's put our RAM into the motherboard. I want to get it in before I put the cooler in. That way I'm not kind of fighting clearance there a little bit. And that's also the reason why I decided to go with this reduced height, or really no RGB version of these RAM sticks and that. So that way I wasn't tempting fate in terms of the height of it interfering with the cooler. And of course, since this is a server build, those fancy RGB things is not really a concern. So to add the RAM into the slots, we first need to figure out which slots we need to use. Now, the motherboard documentation would tell that, but we can also see silk screened on here very closely is directions on which of the particular slots should be used first. So we can see that it's these two slots right here, the A2 and the B2. Now the first thing I'm going to do is unlock the lever. On this particular motherboard, the levers only unlock on one side. This side is fixed. Then we take our RAM stick and we need to figure out which orientation it goes in based on this slot right here going into the lining up with this connection. So in this particular case, I believe it is this direction. And we just slide them down in and till we hear a click. And we make sure this particular level is good and tight on it. And now we'll do the second one. And it also clicks into place. For CPU cooling, we're going to use the Thermalright Phantom Spirit 120 SE. From reading online and various different reviews, this cooler actually gets a lot of nods for its effectiveness, and yet it's a really cheap price. And despite my server case supporting lots of different liquid cooling and the fact that my previous builds has always been with custom water cooling, and that I decided for this server build to go with the simplicity of air. We can always upgrade later if necessary. Now we do need to ensure that this cooler will actually fit inside the case. So if we look at the specs of the cooler itself, it says it's 154 millimeters high. While looking at the specs within the case, we can see that with the graphics or the GPU retainer on, 181 millimeters is the max height supported. So we should be okay in that regard. Now the directions that came with the cooler says the first we need to place this bracket on the back of it. And this bracket says LGA 1700. Now we actually have an LGA 1851, but the two are equivalent when it comes to the bracketry. So we just simply, first we have to take off the pieces of plastic on the back. That gives us a little bit of ease so it can stick to the back side of the motherboard. And then we simply insert it inside the slots right here and here, such that these protrude out on the other side. Next, it says we need to install these particular spacers on the things protruding out. So we're just going to head and install those in each one of these locations. That one was a little hard. All right. Now, the next we need to place this bracket across the area right here and that. And the directions show that the end of this has an elongated slot, and we need to place the screw into the middle of it. So in order to do that, we place the bracket onto spacers that we put in, and then we insert the screws down inside it. And I'm going to head and do both sides and get them started so we can line it up. I'll use my fingers to start out. Okay, and then do the other side. So I'll place that there, and again, move these down just finger tight at the beginning. And then finally we're going to use the screwdriver. I'll hold it in place where I want it, and I'll use the screwdriver to bring it on down tight. I'm not going to make it super tight. I don't want to break anything, but at the same time I want a nice firm connection. Now when attaching the cooler to the CPU, we need some sort of interface between it, normally like a thermal paste. And the thermal paste that actually comes with the cooler, the TF7 here, is actually rated pretty well in that. So one could use this and feel confident that it's going to work pretty well for the cooler in that. But I'm going to do something a little different. I'm actually going to use the Thermal Grizzly Cryo Sheet. Now the Cryo Sheet is like a thin little piece of paper. It almost looks like a piece of paper, but it's really a graphene sheet that you just lay on top of the CPU, And that works functionally the same as thermal paste in that it ensures there's good contact between the CPU itself and the bottom of the cooler, and it has a really good thermal conductivity in terms of moving the heat from the CPU up into the cooler in that. And ultimately, what this is going to give me easier down the road in terms of changing out. Let's say I want to change the cooler to something different. Perhaps I want to go water cooling since the case supports it. I can easily take off the tower cooler, and this little graphene sheet could be reused. Or it also makes it less maintenance in that. So normally when you have thermal paste, every couple of years it might dry out, or what they call might push out, where the expansion and contraction of heating up and cooling down slowly pushes the paste off the sides. And that with this graphene sheet, we shouldn't have that kind of problem, so it becomes more or less maintenance free. Before we can install the tower, we have to put this cryo sheet onto the CPU. And now, right now, the cryo sheet itself, you can see it inside this plastic. It's made out of graphene, and from what my understanding is extremely fragile. So if one were to take it out of the plastic and manipulate it too much, it might actually kind of break apart. So what I'm going to do first is look at the size and the dimension of this square graphene versus the actual CPU itself. Now if I place it down on top of it, as so, I can see that it overlaps the width of the CPU. This dimension looks good to me, but it looks like an overlap on it. And from what also I understand is the graphene is electrically conductive. So while from a heating transfer point of view, it's not a problem if it overlaps, it might droop down, and if it droops down, it might touch something which could short it out. And in fact, if I were to take this back out again, and we were to look at the socket itself, we can see that there's surface-mounted devices inside on the sides of the CPU, which would be concerning for me if the graphene were to droop down there. So we're going to have to cut it to the right width of the CPU itself. Now, one thing I note on looking at this, I don't know if we can get it on camera or not, but there seems to be kind of a grain to this. Meaning that there's like lines that I'm seeing across it in a particular direction. Now, I don't know for a fact, because I don't know that much about graphene, but in my days of used to do woodworking, I certainly remember cutting with the grain is easier than cutting across the grain. So what I'm going to do is going to put this down onto the CPU. I'm going to set one side just barely overlapping the edge of it, but not overlapping enough to really sag down and touch the surface of it. And I'm going to make sure the grain is going the direction of which I intend to cut. And I'm going to take this marker, and I'm just going to mark on the plastic, holding it down here, where I want to do the cut. So right about there. Now again, I have the plastic on both sides of this graphene. So next I'm going to take a pair of scissors and carefully cut about where I marked, staying parallel with the lines of the grain of the graphene. Okay, and now if I place this back down, it is a much better fit than it was before. So now with that, we can place graphene, take the graphene out of the plastic. Well, actually, before I take it out of the plastic, I want to clean the socket itself and that. So I happen to have some cleaner that's usually used to clean off paste. Bought it many years ago. It seems to be lasting forever. It has a two-step process, one sort of a cleaner and the other is an actual purifier on it. So I'm just going to put a couple drops on it and then take a lint-free cloth and just wipe it off. And what I'm doing is just making sure any oils and stuff from my finger has been removed from it. Now, I don't know for sure if that really affects the graphene itself, but it certainly affects the paste. But it can't hurt having a clean lid on the CPU. And I'll just wipe that one as well. And we're done. So now is the tricky part. I'm going to take the graphene out of the plastic and carefully place it onto the CPU. And carefully lining it up to cover. There. Now, before I put the cooler itself down on top of it, first of all, we have to remove this plastic on the bottom. There's a giant warning on it telling you to remove it. And I will carefully place this on top. Now, the goal is not to place it and maneuver it and tilt it, because that could move the paper around. So I'm going to try to line this up on first try here, exactly where it needs to go. And then I will use a long screwdriver. I had to use a different screwdriver because the length here is kind of a skinny channel. And I will push down and install a little bit on each side. Make sure I get that side in okay. There we go. So I do a couple turns on each side and slowly add more pressure. That way we have even pressure all the way down. And then finally we want to install the fans onto the cooler itself. So here are the fans. It includes two, has a single PWM wire that comes off it. We're going to want to install one here on this side and one in the middle. That way the air can flow across to the exhaust fan. And we get our choice when we install it where to place the wire. We're going to want to plug it in to the two headers here. The motherboard actually has two headers for the CPU fan, a regular one and an optional one. So we're just going to go ahead and use both of those connections and that. The fan does come with a Y connector, and we could use that as well, but I'm not going to actually use it since the motherboard has two connection points and it gives me a little bit less wire to manage on that. So I'm going to stick it so the wire is down and to the far side, coming out of the fan on the far side away from the plug. That way we're using more of the length. And we have to just install these brackets. So these brackets just clip in to the side of the fan, into the fan hole here. One on that side, and one on this side. And we go ahead and just clip it right into the fan. Pull it tight here. Pardon the head. There we go. There's one. And then we do the same for the second fan. All right, the last step is we just go ahead and connect them into the socket. So perfect fit wire on that particular one. And this other one Looks like it's going to fit in between the rams. Let's go ahead and tie this guy in. You can see how close it fits on that ram. To install the motherboard onto the motherboard tray, we need to first put the standoff hardware onto the tray itself. And then once we put the motherboard on top of the standoffs, then we can use these screws to tie down the motherboard. Now, conveniently, they have placed letter labels on all the various holes in the tray so we can know which ones we need. Now, in this particular case, we have a standard ATX motherboard, so what I'm looking for are these letter A's that are on this tray telling me where to place the standoffs. Now, there's one additional A over here, but looking on the motherboard itself, I don't actually have the screw holes. So if I were to hold this over, you can see we have 3 holes there, 3 holes in the middle, and 3 holes on the top right here, and no other holes in the case other than those. So I am going to use these 3 holes here, 3 in the middle, and then finally 3 right here on the edge. And I will ignore this one since there isn't that same hole in the motherboard itself. So this is just as simply as screwing it into the tray. Just do it all by hand. And just to make sure, I'm going to lock them down with the plier too. Just give them a little quarter turn. Alright, with that's done, next we can place the motherboard onto the standoff itself. I'm just lining, try to keep my head out of the shot, just lining up the holes where we have our standoffs. And then we can pull the screws down. Screw. And just to line everything up, I like to do things crisscross, so I went ahead and put this screw in too. And I'm going to do one on this corner. And finally, last screw right up here at the top. Now you can see we can have the motherboard attached to the tray. Nice air gap on this, because this almost makes for a nice test bed to try things out. So usually when I do builds, I prefer to test things along the way as best as I can. So instead of building everything into the case all at once and then throwing the switch and see if it works, I like to kind of build my way up. This right here represents the minimum that we would need to try something out, where we got the motherboard, the CPU, the cooler on top, and the RAM. So let's go ahead and connect it up to the power supply and see if we can get this much functional. Okay, Future Jim here. I wanted to film a bit of an outtake so it wasn't so abrupt at the end of this part 1, and that the build video, the detail is more than I anticipated, so instead of making one gargantuan length video, I decided to break it up into 3 parts. Next time I plan on covering the power on, the testing of the motherboard that you just saw me construct, as well as some of the storage and the fan strategy of the case and that. So I hope to catch you on my next part 2.